Okay, so I'm starting. Uh, a very good evening to one and all present here. My name is Manis Jain, and I am a second year undergrad pursuing metallurgical engineering and material sciences from IIT Bombay. I welcome you all on behalf of Think India IIT Bombay. I would like to take this opportunity to introduce our moderator for the talks today, Professor Sudarshan Kumar, HOD, Department of Aerospace Engineering, IIT Bombay, is a mammoth in the field. He pursued his bachelor's in mechanical engineering from Dr. BAM University, Aurangabad, followed by master's and PhD in aerospace engineering from IISc Bangalore. His sincere efforts towards his field quickly rose him through the ranks, and his various research papers are a source of enlightenment. He is a profound researcher, professor, and a winner of various prestigious national and international awards for his contribution to his field and carrying further the baton of science and engineering. He is among the boards of governors in IIT Jammu and a visitor's nominee for the Aerospace Department in IIT Madras and a crucial and integral part of the IIT Bombay fraternity. I welcome you, sir, and request you to take over the proceedings of this event. We also have Professor. I'm sorry, I sorry. I'm so sorry. We also have Professor A.K. Suresh from Department of Chemical Engineering, and also the former Deputy Director of IIT Bombay amongst us. I welcome you, sir, and thank you so much for your sincere presence. I would request Professor Sudarshan to take over the meeting and carry on with the proceedings. Thank you so much, sir.
Yeah, thank you, Manas. It's my privilege to introduce my so-called senior in the lab, Dr. Debasis Chakraborty, who currently have joined now in our department at IIT Bombay. I would like to speak few words about him. That he did his masters from IIT Kharagpur, and then he joined VSSC Trivandrum. In one of the meetings where he was presenting some of his work, he had a meeting with Professor H.S. Mukunda of IISc, where Professor Mukunda way back in 90s told him that why don't you take up the problem of supersonic combustion, which is very crucial for the future of the country, and you can pursue your PhD in this. So with that motivation, Professor Devashish Chakraborty in 1992 joined in IISc Bangalore, and he was perhaps the first in the country to start the direct numerical simulation of these high-speed flows. And in 1998, he completed his PhD on supersonic mixing layers, both reacting, non-reacting. And that was a kind of a marvelous piece of work in the field. And based on this work, when the work on hypersonic, this technology demonstrator was started in DRDL, he moved from VSSC to DRDL. And there he established a very strong group in the field of computational mechanics, more so in CFD. And he made various contributions to the field over last 35 years in both aerodynamics and propulsion design problems, both at the ISRO satellite launch vehicles as well as the strategic and tactical missiles of DRDO. He developed many industry standard compressible CFD codes, both RANs and LES, for aerodynamic and propulsion characterization of different aerospace vehicles, both external and internal flows that help the design to proceed to a direction where he was able to accurately predict the experimental results or experimental expectations beforehand. So based on many of his inputs, the scientists in the range were able to make significant changes and bring in the modifications in the design so that they get best of the product in the field. After superannuation, he had joined Aerospace Engineering Department, IIT Bombay, as a professor, and he has taken over as director of Center of Propulsion Technology, which is a DRDO initiative for direct research in advanced propulsion technology. He has worked for this HSTDV, which is Hypersonic Technology Demonstrator Vehicle, for over 2 decades, excluding his PhD thesis. And he has made many significant contributions, including the successful flight trial last month. If you look at his publication records, he has over 240 publications in reputed national and international journals and conferences. He is fellow of many prestigious professional bodies, including Indian National Academy of Engineering, Telangana Academy of Sciences, Institution of Engineers, and so on. He has many awards, like some of them to mention: DRDO Scientist of the Year, DRDO Award for Best Innovation Futuristic Development, Technology Group Award, and so on. He is also reviewer of many of the committees of national and international importance, member of editorial board for many journals, and he has interests in aerodynamics, propulsion, CFD, RAMS alias grid-free methods, combustion, high-speed reacting flows, modeling of turbulence, chemistry interaction, unsteady flows, and so on. With this, I hand over the stage to Professor Debasis Chakraborty, and I know that his talk will be like motivating you from the all spheres of the technology. Thank you. So, Professor Debasis.
Thank you, Professor Sudarshan, for your nice words. Whether I don't know whether I am really fit for that. Coming back to the today's talk, I will be explaining you my experience of the development of this hypersonic technology demonstrator, and which is employing Scramjet engine. And as the Professor Sudarshan told, that my journey in understanding this problem started from 1988, and of course our teacher who has introduced me this subject, and then we continued, and my learning and my studies are still continuing in this area. Coming back to this today's talk, we will be this vehicle has been developed totally indigenously. We talk about this Atmanirbhar Bharat. It is the examples of the activity. Last 2 decades, really all the design activities of this hypersonic technology demonstrator vehicle has happened in the country. Because we didn't have the test facilities, we went abroad to test those various aspects of those vehicles. But the design, realization, everything has happened in our country. So really, it is a very proud moment for me, and I'm really very much excited to share my experience with you all. And I'm just sharing my presentation. Is it visible?
Yes, it is visible.
Yes,
Please
yes.
go ahead.
Okay. The title you all know: Hypersonic Missiles, a Game Changer for the Modern Warfare. I have structured the presentation in the following way. Because a lot of students are there, I thought that I will be going in little fundamentals. I'll be explaining the air-breathing propulsion system in the various flight regimes. Then, what is the advantage of these hypersonic missiles in the atmospheric flight for our defense requirement? Various countries are developing these hypersonic missiles. Mostly they are of the 2 types: hypersonic light vehicle and hypersonic air-breathing cruise missiles. What is the world scenario? Then I will be talking about the Indian initiative of the hypersonic technology demonstrator. All of you must have these things read in the paper and seen in the news that last month we have successfully tested, and I will be touching upon my own contribution as a scientist or as an engineer, whatever the problem I have solved in that these complex technologies. There are many complex technologies. Only 2 I will be explaining how these things are numerical techniques, that computational fluid dynamics, what is the these things, a tool, what we have developed from a academic tool to a design tool. And that is this vehicle is also a journey of that this effort. And now coming back to this, how an aerospace vehicle move in the air? There are 4 forces: thrust, drag, lift, and weight. Thrust must overcome the drag, and lift must exceed the weight. If these conditions are met, then a vehicle can fly in the air. And these things, what is the thrust? It is this thing that the propulsion, aerospace propulsion, in engine, the fuels are burned, and this hot gas is expanded through a nozzle, or sometimes some portion of the things is used to run the turbine, and some portion is to produce the thrust. And this concept of thrust is very simple. This is only that based on the 2 Newton's laws of motions. That the second law, force is equal to mass into acceleration, and third law, every action there is an equal and opposite reaction. And the thrust is nothing but the difference between the inflow momentum and the outflow momentum. And in aerospace propulsion, the chemical energy that which is there in the fuel is converted into thermal energy by reaction, and the thermal energy is converted into kinetic energy. And for air breathing engine, thrust is defined. This is the m dot is the mass flow rate, and the v velocity, p pressure, a the area. Now, if you look at all the aerospace engines, they can be classified into 2 categories. This is the air breathing engines and the rocket engines. In the air breathing engines, we use atmospheric oxygen to burn the fuel, and in the rocket, we carry the oxidizer and fuel on board. So that's why, because we are not carrying the oxidizer and you are using the atmospheric oxygen, air breathing engine is very, very efficient compared to the rocket engine. And that you look at it, the various kinds of air breathing engines are there: turbojet, turbofan, turbosat, turboprop. Then in a high, that is, these are all the low speed region. And if we increase the speed, because man's aspiration to fly at higher and higher speed is always there, and that is a challenging. And this is in a higher speed we can get the Ramjets. Ramjet, briefly I will explain that thing. And the other area is the solid rocket, liquid rocket, hybrid rocket. I will not be touching about the rocket propulsion in today's lecture. Now, how this like we are flying in the aircraft. How the engine works? That the flow comes enter into this thing engine through a diffuser, the intake. Then this flow in the compressor, the pressure is increases. We increase the pressure. Then that high pressure gas, we put it in a burner, that is the combustor, and there we get the high temperature. That high temperature, high pressure gas we use to run the turbine, and turbine is required to run the compressor. And this hot gas we just expand through the nozzle to get the thrust. And this is the working principle of the turbojet engine. The similar is that like what I'm just I told it: inlet, compressor, burner, nozzles. Now, if you increase the speed, really, then if this suppose I'm going into Mach 2, that the twice the speed of sound, means nearly 600-700 meter per second. That is the velocity. And if we can compress the flow to a subsonic value, we get a pressure rise what we get across a compressor. So that means if we fly at a higher speed and if we decelerate the flow properly through a intake, we don't require a compressor. If we don't require a compressor, we don't require a turbine. So that all the rotary systems can be dispensed with. We get a very, very simple system: intake, a combustor, and a nozzle. So this is a very, very efficient propulsion system in the range of the Mach 2.5 to Mach 2 to 5. And it has to be first boosted, and then ramjet is ignited and the operation starts. So there are many types of ramjet. In DRDO, we developed the few Ramjet powered missiles, and you must have heard the names Akash, BrahMos, which has been these things put into the services. And some of the flight video I would like to share with you. This is the Akash flight trial, very short video. This is the pilotless target aircraft. This is the target. We will be hitting it by just firing the missiles.
And this is the first player and confirm.
And you will be seeing the two missiles will be going in tandem. That is called the salvo firing. This is the first missile. And after a few seconds, the second missiles also will be fired. Because you don't want to take the chance. And it will be following the target. And you see at the end, it will be hitting the target directly. This is the hit of the target. There is a lot of other stories. Sometimes I will be telling you how it works. And really, we have worked quite a long time to develop. This is also totally indigenous system, and this has been deployed in various parts of our country to safeguard the territorial integrity of the country. And it is one of the major workforce for our both Army and the Air Force. And another one video I would like to show, that is the liquid fuel ramjet. This is BrahMos. This has been developed jointly with the Russians. This is some of the flight trial. Now, we have mastered the technology of the Ramjet propulsion. Now, if we increase the speed further, like up to, I told you, Ramjet is 2 to 5, is a very, very good in this Mach number range. It is a very good propulsion system, very good efficient system. But if you want to fly even higher speed, suppose we get into Mach number 6. So if we again decelerate the flow, the pressure is increasing, that is desirable. But at the same time, temperature is also increasing. In a very high speed flows, if the temperature increases, we cannot add fuel to this to that stream. So on the other hand, we cannot, because then most of the energy will go in the dissociation. So that in the other hand, we cannot decelerate the flow to a subsonic value. So we have to keep the flow supersonic, and we have to add fuel, and the reaction has to take place. And now, if the speed is more, that the residence time of this thing's oxidizer in the combustor is very, very small. So in that short time, how we will be igniting that fuel and release the energy? That is the real challenge. And this is the Scramjet propulsion is, I mean to say, state-of-the-art technology. Very few countries have mastered that technology. And this is the power plant of every hypersonic missiles. Now, if you look at the performance, I've just compared that. Now, I told it that various Mach number regions, various propulsion system works. So that this is the turbojet, this is the Ramjet 225, then the Scramjet can work for a longer, in the larger Mach number range. And the performance wise, also it is much superior than the rocket engine. Just to give you an example, that for a rocket, liquid or the solid rocket, the ISP, the specific impulse, which is the parameter for every fuel, is of the order of 300. Maximum that cryogenic fuel will get it 400, 450. But in these things, in a air breathing, I mean to say, Scramjet or the Ramjet, will get the ISP of the order of thousands or more. And why we need a hypersonic missiles in the atmospheric flight? First thing is the faster response. Suppose we have to travel 300 kilometers and we have to attack some of the enemy position. And if we go at the subsonic speed, like some of the 800 kilometer per hour, will take 22.5 minutes. And if we increase the speed, it will be reducing to 5.2 minutes, and the hypersonic speed 2.2 minutes. Now, this advantage will be more if the distances are increases. If we travel distance, have to travel 1,000 kilometers in a subsonic missile, it will take 75 minutes, and supersonic missiles like BrahMos Mach 2.8, it will take 17 minutes, and in the hypersonic Mach 6.5, what we are trying to develop, it will take 8.8 minutes. I'd like to share one small incident with you. In 1998, American intelligence has found out the hideout of Osama bin Laden, the terrorist. So, and then they fired their Tomahawk missiles from that Persian position. This the Tomahawk missiles, it was traveling in a subsonic speed, and it nearly took 2 hours to come from that Persian base to hit these caves in Afghanistan. By the time they also got that news, and they left that cave. Although missiles came and destroyed those caves, but nothing could be done to Osama bin Laden. So, and then the think tank thought that if they would have a hypersonic missiles, it could have destroyed the things within very short time, within 5 minutes, and then the WTC event would not have happened. So this is the advantage, one of the big advantage, that the quick response time. Second advantage of these hypersonic missiles, that enemy radars will not be able to track. See, you look at it. Now, if we are this thing firing all those our Agni missiles. It is going above the atmosphere and coming down, hitting the target. So the radar can track it quite early in their flight. The moment it increases the altitude, then it can see that some enemy missiles are coming, and you can have the ballistic missile defense. So to neutralize this effect. But for a hypersonic missiles, it will be traveling at the altitude of 30 kilometers, and when the radar will be tracking it, the enemy doesn't have any time to make some countermeasures. They are calling suppression of the enemy air defense, because you require some preparation time. When you know that something is coming, and you have to prepare your arsenal, but before that, the decision is taken, they're destroyed. So this is the major two advantage for the time critical target, and then these things, you are stealth. I mean to say, it is not possible to get detected. Now, another one advantage is there, because it is traveling with a very, very high speed, like Mach 6, that is having a tremendous the kinetic energy. And then the penetration power is also very, very high. So these two types of target, like the time critical target, like enemy force in transit, terrorists fleeing in a vehicle, mobile theater missile launchers, mobile surface to air missiles, high value military cargo, mobile command and control vehicles, and then some of the hard and deeply bodied targets, that biological, chemical, nuclear weapons, production, assembly and the storage facilities, hardened aircraft soldiers, centers, underground C4I facilities, and this goes on, this list goes on. So for this kind of targets, the conventional missiles are not very, very useful. We have to develop hypersonic missiles for this. And if you look at there are two types of hypersonic missiles. One is called the hypersonic glide vehicle. In the hypersonic glide vehicle, what do? We take the missiles at some altitude, and then they do the aerodynamic maneuvering, come back and hit the target. But there is no propulsion. But on the other hand, in the hypersonic cruise missiles, till the end of the target, we are having active propulsion. So if you are having the propulsion, you can maneuver the missiles much better. So hypersonic glide vehicle, by higher speed, it is avoiding these things, any target. And hypersonic cruise missiles, it is having both speed as well as the power so that it can maneuver. And if you look at the world scenario in hypersonic glide vehicle, Russia has developed Avangard. It is reaches speed up to Mach 27. These things, it was developed at 15-16 time frame. And USA has developed HTV-2. And this is also, it will go up to Mach 20. And range is of the order of 7,000 kilometers. China has also tested that U-14 in 2017. We are in India also. We are developing the hypersonic glide vehicle. I'm not going to talk about it, but in this presentation, I will be mostly discuss the issues of the hypersonic air-breathing cruise missiles. And now in this hypersonic cruise missiles, this USA has developed two major programs. One is called X-43, that is with the hydrogen fuel, and one is X-51, that is with the hydrocarbon fuel. For the military application, hydrogen fuel is not preferred because of the space limitations. Because hydrogen, it requires very, very huge tank, so the drag will be more. And for the space program, hydrogen can be used. In this mission, what they have done, they have taken the booster and the cruise vehicle on the B-52 bomber. They have released it at nearly Mach 0.8 to 1.2. Then one Pegasus booster has taken it to that Mach 6 or Mach 7 condition, and they have demonstrated the operation of the X-43. Then X-51, they have taken that is the hydrocarbon fuel scramjet, and they are developing it for the missile applications. So this testing was also carried out in this thing around 2012. And what they have done, this also they have carried it under the wing of the B-52, and along with the booster. The booster 0.8 to Mach 4.8 they have taken, and 4.8 to 5.1 they have accelerated, and around nearly 210 seconds flight was there. So just the profile. Now you look at it, they have this is the launch from the B-52 at Mach 0.8, then the booster burnout and the separation at Mach 4.8, and Mach 4.8 to 5.1. This is around 210 seconds. This is the flight. This is the longest operation of the Scramjet engine worldwide till today. And just to summarize, there are a lot of these countries are developing. It started with the National Aerospace plane in USA, and a lot of technology was developed, but finally this project was stopped, and there was no flight trial. NASA and I mean to say like USA and Russia together, they have developed the NASA Siam test. Australia, they have done some flight trials for the Scramjet engine, but that doesn't have much practical relevance because it is in a captive mode. They have put the Scramjet engine in a sounding rocket and tested the Scramjet engine. High Fire, Australia is again another one smaller scale. X-51, I have already told. Some 2-3 years back, ISRO has also tested the Scramjet engine. That is also captive trial that they have put the two engine on a sounding rocket, and without separating that the engine, they have tested and they have demonstrated the Scramjet engine. And LEA France also they are having a program, and HSTDV, I will be talking more about it. And Kinjal is a Chinese these things they are telling that developing those Scramjet engine, and Zircon is the Russian Scramjet engine. So that not much information is available in this open literature. But that's why that in summarizing, only a few practical flight tests of the hypersonic air-breathing cruise vehicle have been conducted worldwide. France, UK, Germany, China, they are also putting a lot of effort for the design, development and testing of the Scramjet combustor for hypersonic vehicle. The flight trial of the hypersonic air-breathing cruise vehicle X-51 by USA for 210-second duration is close to the hypersonic weaponization program. And last month, September 7, we have test flown the HSTDV, which is an autonomous functioning of a vehicle integrated scramjet engine with hydrocarbon fuel for 24 seconds. Now, mostly I'll be talking about the design of that vehicle leading to the flight trial. Earlier you have seen that US, they have taken the vehicle along with the booster to some altitude by a aircraft. They are having a very, very powerful aircraft called B-52. In our country, we don't have that kind of powerful aircraft. So, but we have to test the Scramjet engine. What we thought, we will be taking the Scramjet engine in that altitude where it can, that in that Mach number and that altitude, because Scramjet engine can work above Mach 5. So we, and at the altitude of around 30 kilometers. So we will be carrying that whole vehicle, and then we'll be releasing it there and test the functioning of these things, so that to demonstrate the Scramjet technology. So we have taken a Ogni booster, and over that we have put those this is cruise vehicle. Now our material technology is also not that much developed. So in order to protect the vehicle from the aerodynamic heating during the ascent phase, we had to cover it with a heat shield. And that heat shield separation, that is also becoming a very, very big challenge. Because in this, to say, strong atmosphere, where 30 kilometers atmosphere, the heat shield separation poses very, very complex problem. You may be seeing that satellite launch vehicle or the ISRO, they also separate the heat shield, but they separate the heat shield at 110 kilometers when there is no atmosphere. But here we have to separate all those things in a very, very sensible atmosphere that creates very, very, I'm going to say, serious challenge, and they are all mission critical. And now how we have solved that problem, how we have designed it, and because in our country we don't have that kind of test facility to do that, those testing, we have to depend on this, our numerical methods. I will explain that thing. And this whole this thing's concept of this this HSTDV through a animation, I would like to explain. This is the cruise vehicle where that Scramjet technology will be tested with the hydrocarbon fuel. There are a lot of critical technologies like hypersonic aerothermodynamics. These are that vehicle forebody, intake, combustor, wing, tail, and the Mach 6.5. This is the launch booster. We have put the cruise vehicle over it, covered it with the heat shield, and then we are firing from the ground with a launcher, ground launcher. Then after the burnout, it was coasting is taking place and the gaining altitude. We are taking the turn to make it horizontal. Then when the Mach number 6.5 is reached, then the heat shields, they are separated. There are two weight. One is the nose panel, one is the cylindrical panel. Then the cruise vehicle is exposed. It is separate, that all those control surfaces are deployed, and it is separated from the launch vehicle. Now it is autonomous aircraft-like structures. The Scramjet engine is ignited, and that now this same thing. These are the hypersonic test vehicle, the critical technologies, the hot structures, hypersonic aerodynamics and aerothermodynamics, high temperature material, hydrocarbon fuel Scramjet engine, endothermic fuel development. These are the typical challenges in developing this kind of vehicle. Like that, there are a lot of hardware, launch vehicle hardware. This is the heat shield. There we call it L1, L2. Then there is an adapter. Then this is the booster and the base route. It is required to control the vehicle. Then there are all of interstage, that avionics, and in the cruise vehicles also there are various sections. First two section, the ballast, that in the future when the missiles will be developed, this thing payload will be kept, and this transmitter, this all the avionics. Then this in the scramjet engine fuel fed system. Then all those controller to control the wing and the tail, and all those systems are available. We have to do number of tests because it goes in a very severe atmospheric conditions. Dynamic pressure is quite high, so the temperature is quite great. So under those conditions, those structures should withstand. So a lot of thermostructural tests we are doing it. Lot of ground resonance tests we are doing it to find out the control structure interactions. Then that this is the panel separation. I'll be going into explaining in details how we have qualified these things without any wind tunnel, how we have done the test. Then some of the tests we have to do it in the Russia, because when we are developing this vehicle, there was no hypersonic wind tunnel in our country, big hypersonic. Of course, we have developed two big hypersonic wind tunnel in our country, one at DRDL, one at VSSC. In our next development, we need not go to Russia for doing those tests. And the Scramjet combustor, mostly we have done on ground, and some of the free jet tests we have done, and then a lot of other that vehicle tests we have carried out for this cruise vehicle. And number of technologies, new technologies we have developed during the development of this project. This one is the aerothermodynamics, configuration, design, and testing. This is then we can tell it with confidence we have mastered this technology. Any kind of hypersonic vehicle we can design. We have developed the CFD capabilities, and they are all in-house development. I will be explaining some of the capabilities what we have developed. The panel separation dynamics, that is also a big challenge, and we have these things developed develop those technologies. Hypersonic air intake characterization, scramjet combustor design, hot structure design, split composite airframe, coating, material characterization. This number of technologies we have developed. And out of these things today, I will be explaining two technologies, the panel separation dynamics and the scramjet combustor design, where I was directly involved. And in fact, I have worked for nearly 18 years on those technologies. So I'll be just explaining how we have done this work. This fairing separation studies of this hypersonic technology demonstrator vehicle. I have explained that in order to protect the cruise vehicle against the aerodynamic heating, we are protecting it by a heat shield, and the heat shield has to be separated. And these are all the mission critical. While separating, if these panels hit the body, the mission will be that will be disastrous. A small force in that this is what it will be imparting in the vehicle, and we will not be able to control it. And here we have developed a grid-free methodology in-house in DRDL, and this is a unique development and one of the best in the world, I should say. Here, these things we are the grid-free means we are not using any structured or the unstructured grid. This is we are working on a collection of the points. So that way, that any kind of complex geometries we can model without any problem. So this is the beauty of this grid-free Euler solver. If I give a chance, I will be talking about this development in different the forum. And now how these panels will be separated. There are this total heat shield has been divided into two, and one is the nose panels, one is the cylindrical panel. And if you look at it, the nose panels, they are asymmetry. And one side there is a bigger structure, other side it is that nose cap is there in one side is not there. So it opens in asymmetrically. So that gives more problem. And now how it will be opening, what will be the hinge, how we will be designing it, and then how they will be separating, at what time we will be initiate the separation. These first two panels will go. After that, the cylindrical panel will be opened and they will be separated. And once that is done, that the cruise vehicle has to be separated from the launch vehicle. So these are all mission critical. And how we have solved this problem, let us say. This what we have done that this is the grid strip date before blanking, this is the grid size, and this is the after blanking. Thorough validation of this methodology has been done before applying it to this date. And this is the geometry. Here in doing those simulations, we have not made any modification in the geometry. The geometry as they are fabricated, that CAD file we are doing it and making use it in our simulations. You look at it, first these panels will be hinged. After a certain time, the hinge will be opened and these panels will be separated. And then we are following their angular rate, angle, and during these things they're continuously increasing. At this time it is releasing, and then these rates are this decreasing, and it is within our control. And to explain at the various time instant, this things panel was at 90 millisecond, it was released, and then at the various time, what is the position we are doing it. To explain these things, I'll be showing a small animation how the panels are getting separated. And this is the pressure field over the surface. And through the simulations, we can see that it is safely going out, and it is not affecting this panel. Now, during this the panel separation, it is a challenge to control the vehicle, because these forces will have some adverse impact on the cylindrical panel as well as the main body. How will be the forces and moments has to be calculated accurately, and the control strategies has to be these things worked out. Then similarly, the cylindrical panel also has to be. Then what is the time I should initiate that cylindrical panel separation? And through that also, I'm just showing it one animation. So through our simulations, and similarly, we are showing how these forces and moments. So we are calculating the pressure on the body, and once you know the pressure, then we can find out the all the forces and moments. So the total sequence of the separation, nose panel separation, cylindrical panel separation, this everything has been done through CFD, because when we are designing, we didn't have those testing facility. Now the question is that this is this is our design we have done, but we have to validate those design numbers, and also there are a lot of these things equipment which will be going into the flight, like pyro bolts, the hinges. They have to be qualified under these load conditions. Then we saw there is one sledge facility in one of our DRDL laboratory at Chandigarh called TBRL. There we can fly, we can just in a sledge, we can move the vehicle at a Mach 1.2, and there is nearly 4 kilometer range is there. Then we thought that if we can simulate the dynamic pressure, like when you are going high in the altitude, density is coming down, but the velocity is high. In the ground, I am restricted by the lower velocity, but the density is higher. We have seen if we can these things move that sledge at 0.6, the dynamic pressure between the flight and the ground test are matching. So at least the forces we are able to do these things. Mach number we will not be able to simulate, but the forces which is being experienced by the vehicle will be simulating. And under that condition, if we predict and if we can measure those things, then that will give us the confidence. So then this again, those ground condition Mach point, the flight is 6 and above, but here 0.6 we have simulated, and this thing shown that this is also these things very safely it is separating. Then various pressures we have measured, we predicted, we are getting a very good match between the prediction and the test. Then you look at it. This is the CFD is predict at one location, only on typical location I have shown that P15, that is pressure locations. This is our prediction, and this is the test data. And again, the test, the upper one is the test, lower one is the CFD prediction, and it is one to one it is matching. I would like to show it. I would like to show it once more to tell this, the upper one is the test data, and that is our prediction. It is matching one so nicely, and that has given us the confidence to go with the flight trial without any other test. Now I'll be changing another one problem, that is the how the CFD has been used to design a scramjet combustor. So first, we have taken the numerical methods, whatever we are using. We have validated it the number of cases for the non-reacting flow, various types of wall injection, the start-based combustor, pylon-based combustor, cavity-based combustor. Wherever there is a literature data, we have taken and we have compared our results. And there are nearly 25 different experimental conditions what has been reported in the literature. We have taken, compared. That has given us the confidence that, okay, this is the method, we can use it for our design. I'm not going to describe all those details. They are there in many publications, and these are our own the test. This is something Chinese experiment, and this is NASA did some experiment to validate their CFD codes. And what we see, our code is matching better than their well-known CFD code Vulcan. The various types of chemical models also we have seen, because this hydrocarbon and hydrogen reactions requires a turbulence chemistry interaction model to be developed. That we have done extensive work on it. And this is a Chinese experiment. This is our own DRDL experiment what we have compared. And really, we are very fortunate. That time DRDL authority made it a point, they will not be doing any test unless there is a prediction. So the prediction is always there before doing a test. So that gives this confidence. Then we have seen various turbulence model, which kind of turbulence model we'll be using, and so that has these things we could calibrate our guide. Now, to summary of the validation studies, it says the well-dissolved CFD simulation is capable to capture the essential features of the scramjet combustor flow. The use of the fast chemistry predict the wall pressure higher in the fuel injection zone, but in the divergent portion of the combustor, which is the major thrust producing element, their computation predicts very well. And we could say that whatever we have predicted, and both the test results, both in that in the literature or in the ground-based test, we could predict within 5%. And this SST K omega turbulence model, it has performed better. And that what I told, more than 25 experimental reacting flow conditions were simulated. Now, this tool, we have these things using for the design. When we started designing, the start locations were, has been chosen this way. The 7 starts were taken, and what we did the simulation after see that thing's performance is very bad, combustion efficiency only 51.4, and the thrust is getting 304 kg, and that is not adequate for the mission. Then what we have done, we have just changed the start locations, changed the fuel injection location. In the CFD, the greatest advantage is there. We can know the total flow field. We can see that where there is a fuel is reach, where there is a fuel lean. We can modulate the fuel injection in such a way. We can see that these things temperature is uniform, and we are getting a very good performance from the combustion. So that in all those things in the iteration, in the second iteration, we got the combustion efficiency higher, and thrust is around 400 kg. Then we saw that the last 2 studs are not doing anything, because near the wall that it is not penetrating into the core flow, and the fuel chemical energy is not getting released. So that we have reduced, and we have seen the combustion efficiency has increased, and thrust has which is adequate for our mission. Now, then this combustor was finalized, and we took it to the connected pipe mode test facilities. Although pressure was matching, but there was a problem. This combustor was planned to be work for 20 seconds. After 5 seconds, all the studs are getting melted. Then we have tried it various exotic material like niobium alloy, tungsten alloy, but none of these cases the studs are withstanding more than 5 seconds. So now, then what we thought, what we saw, where is that maximum erosion? There only we are getting the maximum temperature. So then from the CFD, we redistributed the stud locations. Earlier, we are only thinking about the performance point of view, the pressure, whether we are able to get the thrust or not. But the thermal point we are not addressing. So now when we have when we have noticed that problem, we redistributed those studs and the fuel injection pattern. And you could see that earlier that stud locations we are getting very high temperature, but then when we are putting it in these things, here we are trying to see that where I will be allowing the reaction to take place. The reaction should not take place very close to the surface. Very close to the surface. So we can put those injector in such a way, because that kerosene we are injecting, it will take some time to evaporate. Before that, it will come to the gas phase, and then the reaction will take place. So this way we are we modulated in such a way that the temperature on the studs are reduced. So because this is what we could do, because we are seeing the flow field totally from one end to the other end, various cross section. I know what is the flow field. Similarly, the kerosene and air reaction gives you carbon dioxide. Where the carbon dioxide, here there is no reaction. Now the reaction is starting, and at the end, I see that whether the reaction is complete, and then there is a fuel and oxidizer are well mixed or not. And design was progressively improved by CFD through relocation of the stud and fuel injection system to obtain performance parameters required for that. Originally, we started with the 74% combustion efficiency, thrust was 442. And with the relocation of the studs, relocation of the fuel day, we get nearly 500 kg thrust. And now I mean to say that new design was tested. Earlier, niobium alloy, tungsten alloy were all getting melted. Now with the stainless steel, we could do the test for 20 seconds. The same hardware was tested 5-6 times, and the same hardware was also the test flow. And these things, by modulating the fuel flow to understanding of the flow inside the combustor, has helped us to solve this thermal problem. And you can look at it, whatever the prediction, whatever the measure, it has been matched very nicely. Then that was done with the single module, the 2 module, we have done the prediction. Whatever the experiments they are doing and whatever the prediction they are doing, they are all matching. Another one, the important problem in this thing, high-speed propulsion, aerodynamics and propulsion are strongly coupled. You cannot solve it separately. In a rocket propulsion, we can separately, we can do the aerodynamics, separately we can do the propulsion. But the air-breathing propulsion, they should be done simultaneously, because intake also give you some forces. The nozzle cowl, they will be also giving the forces. The total aero propulsive parameter has to be solved, I mean to say, in one go. So then we have taken the cruise vehicle and make those this is a structured grid. There is a issue in the reacting flow calculation. We cannot use the unstructured grid, because unstructured grid, our life will be very, very simple. But in the reacting flow calculation, because the flow is not aligned to the grid, then there will be lot of artificial diffusion, and that can participate in this reaction and can give a higher performance, which really will not be getting it. After understanding it, we have made a structured grid, and these cases, one case it took more than 2 to 3 months to make a grid, and then another 2 months to run it in a 3000 core machines in DRDO. And then we can know that what are the flow parameters, what is the Mach number, what is the static pressure, static temperature. Then in the reacting flow calculation, what is the water mass fraction or the carbon dioxide mass fraction, temperature. So after what kind of effect on this angle of attack, these things at 6-degree angle of attack, what is the performance, and this is the surface pressure, what will be the thrust. Then we have made the total design chart, that various Mach number, various altitude, various angle of attack, what is the performance, what is the thrust, and what is the forces and moments. And that is going into the mission design. Using this CFD generated data, because testing for all those conditions is very, very difficult. So we have now, after this successful flight trials, we are working for a long-range mission where the Scramjet engine, now this we have tested for 24 seconds, but now this has to be worked for 1000 seconds. There are a lot of material issues, lot of issues of this endothermic fuel. The thermal management of these things is for a long duration flight is a very, very the critical issue, and we don't have that kind of mechanism. Materials also has to be developed, and all those critical technology gaps we have identified: starting unstarting characteristics, laminar turbulent transition, endothermic fuel, ignition simulation, active cooling studies, aerothermoelastic studies, droplet breakup, high temperature material. Then we don't have free-jet test facilities. We have to do this multidisciplinary optimization for accurate, efficient design. These technology gaps are planned to be bridged through in-house development and academic interaction through hypersonic vertical of the Center of Propulsion Technologies. In a concluding remark, I would like to tell hypersonic missiles are game changer in the modern warfare. World scenario of hypersonic vehicle, the glide vehicle and the air-breathing cruise missiles is reviewed. We have described the Indian initiative for the technology demonstrator. Many new technologies are developed for the mission. For that, I have just explained 2 technologies. Similar the development, similar success stories are there for the other technologies also. This we have used extensively CFD methods to design this vehicle. We require to do a thorough validation and before it is used in the design exercise. DRDO has declared the long-range hypersonic air-breathing cruise missile as a flagship program. Critical technology gaps are identified for long-range hypersonic cruise missiles, and development of hypersonic air-breathing missiles will ensure air superiority. I will end my presentation with the flight video, what you have seen it.
5, 4, 3, 2, 1, now, +1, +2, and counting off. Particle taken off. Page down confirm. Particle health normal.
Thank you, Professor Debasis Chakraborty, for this talk. I think this was one of the most comprehensive talks discussing all the possible ways or the path which was followed during the development of this technology. I can request a couple of audience if they have any question to be asked on this, although there are a couple of general questions which I have answered in the chat, but if there are any other questions or doubts, we can discuss them. Please unmute yourself and you can speak. Yeah, Suresh.
Good evening, sir.
Yes.
Yeah, please go ahead.
Please go ahead. Please go ahead.
Sir, how budding researchers have a uh, can have a means how can they apply for DRDO for scientist positions at DRDO? How can budding researchers be a part of it?
Occasion that in fact sometimes earlier this recruitment was quite regular, and this DRDO authorities were coming to the various institute for the campus recruitment. But last few years the recruitment has slowed down very significantly. There are some advertisements you can apply against it, and but it is much lower compared to the earlier days.
Yeah, so let me just fill in at top. There is advertisement in the national newspapers. You apply against that advertisement. There is a national level test conducted, followed by interview and so on, and then offers are made. And there are some campus placements also by DRDO. Yes, any other question, please? If there are no more questions, then okay, P. Ramkrishna, yeah.
Good evening, sir. A nice presentation. I saw that in the last but one slide before the conclusions, you had angle of attack versus combustion efficiency.
Yeah.
I was just wondering, why is it that at a higher angle of attack, the combustion efficiency was more? If you could throw...
Yeah, right. The mass flow rate, it depends on the mass flow rate. Higher angle of attack, the mass flow rate increases. That air flow rate, the capture air flow rate increases. That's why the combustion efficiency also increases. Because these things for this vehicle, the combustor is slightly over designed. So this is you can if you look at the mass flow capture for various angle of attack, Mach 6 is the maximum. Is it satisfying you or no?
No. One of the things that I had a doubt was, if mass flow rate is more, mixing becomes an issue, right?
But these things this mixing issue, it will be much higher Mach number. This Mach number, we are seeing that the mixing is very good, and this combustion phenomena is a mixing dominated. And so that's why in that the higher angle of attack also lot of to say three-dimensionality increases, and that also aid mixing.
Okay. Thank you.
Or you can say pray and
yeah, Neeraj here.
The other one.
Mr. Muni Krishna has a question, so I think after that, Neeraj, you can take it up.
Sure.
Yeah, Mr. Muni Krishna. Mr. Muni Krishna, I think seems to be not around. Then Neeraj, you can take it up.
Sure. So, Professor Chakraborty, we can see here that actually the CFD was being heavily relied on, or only they have only relied on CFD for some aspects of such a critical mission. So, are there any other precedents to this, or was this the first time that only CFD was taken as a as an evidence, or as a only CFD was relied on for such a
another one case where I was also very deeply involved is that when a missile is getting separated from a fighter aircraft, here only some test was carried out. There no test was carried out. The designer totally believed in this CFD prediction, and this is the flight pilots. They were insisting before they go take out the sortie, they are asking us to do the prediction, and then with the flight data also we have compared our prediction. It was matching so nicely. and then after the every sortie, this flight pilot will be coming and shaking hand with us and telling your prediction and our experience is so nice. And without the CFD prediction, we will not take out any mission. So that is also very good experience. And if time permits and if the opportunity comes, that experience also I will be able to share.
So you actually do see CFD playing a big role in future tests and developments also.
Sure, absolutely no question about it. And coming back, so just one more point I would like to tell. I was going through one book, but the author is writing that hypersonic vehicle would not have been developed in an era where CFD is not available. That summarizes the confidence.
Yeah. Thank you, Professor Chakraborty. Professor Wilson, you are muted.
Okay, So we have a question from Dr. Muni Krishna. So he wants to know how much this detached ID simulations were used in the design of this HSTDV.
No, we have not used the data study simulations. We have not gone beyond RANs because this thing, although we developed some capabilities for the LES, large eddy simulations, but that is restricted to a small pockets and it was under the developing. Here, all our simulations are based on the RANs. And data study simulations, we have not used in anything. Some of the capabilities we have developed, but that is in R&D mode. But no, the flight the cases we are not using data set. Still, what I should say, RAMS is the workhorse for the aerospace industry. If you look, this in CFD Vision, NASA's CFD Vision 2030, they are telling any higher order method like LES will be used for the whole the vehicle maybe after 2050, not before that. Till that time, we have to depend on the RAMs for the design activities. Research will go on that higher order methods, but the design activities, because what I'm just trying to tell, this your end-to-end simulation of this the hypersonic that cruise vehicle. For 3000 course machine, I have taken more than 3 months. And you can imagine how many cases we have to run. And this computing power for the LES is highly inadequate to do the design calculation. I'm telling it, you can take a small problem, can do research, but giving the design data where people are waiting. And nowadays, this the CFD has matured enough to be used a fashionable academic tool. Now it is this thing's design tool, and whenever we are generating the data, we are telling what is his error band. So that means the design uncertainties can be taken care of. I think I make you understand what is the status of the CFD codes for this in the design houses.
Dr. Debasis Chakraborty, there is another question from Uddhav Tyagi. Can you brief us about the issues we are facing with the development of Kaveri jet engine?
Yeah, Kaveri jet engine, although I don't have much working experience with this Kaveri jet engine, when I have come here in IIT Bombay and taken over the COPT, then I started looking at these problems, particularly the pattern factor or this your combustion, that instability, afterburner instability. Then I could see that the thrust to weight ratio is not allowing that Kaveri engine to be used. But I hope our next endeavor, that AMCA, Advanced Medium Combat Aircraft, there we will be successful to make a design, and we will be putting all our effort, and we have these things. Now, any propulsion devices, I am strong believer of the CFD, and unless these tools are I mean to say sharpened, and these tools are well developed, we cannot make any this gas turbine engine development. either the low speed or the high speed. Now these tools are well developed. I hope in the days to come, our design methodology also will be improving. This scramjet engine complexities is less. There are issue of the flow complexities, but the geometrical complexities are less. We don't have the compression, we don't have the turbine in the scramjet engine. Very, very simple, they flow in a duct. And there, how I will be managing these things, that fuel flow and that temperature, that is only the issue. But here, the components are many, and then the complexities are also much more. There, I think any engine house has taken more than 20 years to develop any flight-worthy engine, and they have taken some few $1 billion. Our investment is also very small, and our patience and our support, organizational support to those teams are not adequate. Are you?
Yes, any other person want to ask a question? I think no more questions. So with this, we can hand over this session back to Manas. Manas, can you take it over? Yes, Manas, are you around?
Some electricity issues. So
Okay.
he will just be back. He just left. Just give him 2 minutes. He'll be back. We can take one question if you want.
Okay. So in the meantime, maybe I can ask a question from Dr. Debasis.
Yes,
so,
sir.
What was the biggest challenge you faced in last 20 years? Which you will say, yes, that was the challenge during the development of this HSTDV technology.
The biggest challenge was to convince my bosses to believe in CFD. So, because whatever we are predicting, nobody was believing. Only after the test, when they are seeing 1-1-2-1 match, and then only they believed. And it took a lot of our time to keep them convincing. Here it is a tool, please use it, and it is a very, very cost-effective tool. So my biggest challenge was to convince my higher-ups that to use CFD more and more. Last 6-7 years of my tenure, that time they are accepting, they are using it, and whatever the facilities we are asking, they are giving it. And the last 4 years back, I made a presentation at the DRDL headquarters for the requirement of a bigger the computing system, and they have sanctioned 11 petaflop without asking any questions. I told that whatever the money I am asking, more than double I have said for your 8. Like sometimes I will be sharing my experience with this Astra separation from Su-30. In the general plan, they're planning 200 flight trials that to test in the various envelope. And with the CFD, they have reduced it to 15, 20, 25 flight trials. So 200 minus 20, and every flight trial costs some 5 crores. So that much money we have saved for the country by using this tool. And then when we ask that give us the money to these things to set up the computer system, immediately they have agreed. And this 11 petaflop machine, when that will be set up, it will be the biggest in the country.
Yeah, Vivek, okay. Mr. Vivek has a question. With India having all different kinds of fighter aircraft platform like Russian, French, US, etc., will the integration of the hypersonic missile have any specific challenge for its integration?
Yeah. Now this is whatever the capability we are developing is the air launched. But if you can have a ground launch, if you can have a air launch capability, there are the two the major technological problem we have to solve. is a variable Mach number scramjet combustor. See, the question is that even you look at it X-51, they have dropped it from the B-52 bomber, very powerful aircraft. So the booster weight is restricting the air launch option, because you have to carry it to Mach 6. How you will be carrying? You require a solid booster. The solid booster weight itself is about around 3.5 ton. If you have to go from 0.8 to say Mach 5.5 with a payload of around 1.5 ton. So it requires around 3.5 ton booster weight. So you don't have that kind of powerful aircraft. The most powerful aircraft India is having is a Su-30 that has come from the Russia. That is the maximum weight it can carry is 2.5 ton. So there we are short because we cannot have any air-launched mission. And another one problem, we have to have a variable Mach number scramjet engine. Like Mach 4 to Mach 6, it should be 8. I need not go to Mach 6. I can take the vehicle at Mach 4 and Mach 4 to the dual mode Ramjet scramjet engine we can operate. But that is a new technology. There we have to modulate the airflow, the fuel flow in such a way. In a subsonic part, we will be in a subsonic combustion, we will be having a thermal throat. In a supersonic combustion, there will be no throat. That is, you have to modulate the fuel flow. We understand those technologies, we understand those principles, but making an engine, demonstrating it, it remains a challenge. And I am very sure that integrating of these hypersonic missiles with the aircraft, it will take another few years before it comes to the practical age. Now, issues are known, but we have to work, we have to develop those technologies, and it takes time.
Okay, there's one more question by Shreyas Lahore. He is a chemistry undergraduate. What are the fields related to chemistry in which DRDO has been working? I guess propellants is one. Maybe you can explain a little more on this.
I can tell it two problems. What really we are looking for a solution. One is the endothermic fuel, because you know the scramjet that I'm interested that any hypersonics, the temperature, the gas temperature Mach 6 if you fly, the adiabatic flame temperature come 2000. This is aerodynamic heating itself. Now if you have to fly, you have to these things use this kerosene and air, that's at 2800 the adiabatic flame temperature. This thermal management is a big issue. How we will be cooling the structure? So there is a concept called endothermic fuel. So this fuel, while passing through those channels, it gets I mean to say that decomposed into the that simpler like ethylene and hydrogen, and it can absorb the heat from the structures. So this kind of endothermic fuel development, what are the mechanism? That is a big issue. Another one, expandable the gas turbine engine. There is a we have to add the fuel into the add to the energy to the fuel. Like, can you use some nanoparticle, nanoboron, microboron in a this aviation kerosene? So we can get a much more energetic fuel. And of course, solid propellant, lot of chemistry problems are there. But related to the scramjet and the expandable turbojet engine, these are the two problems. We don't have enough knowledge base in our country. We need to work on that.
Thank you, Dr. Debasis, for such a nice talk. I think you have listed the challenges which were faced during this talk, and there were also a very important output from this talk, that it was this computational fluid dynamics which has played a very important role in the development of this engine. And based on the experience, I can clearly say that in the future, even the development of the next version of Kaveri, we are going to have the development more through CFD than experiments. However, the CFD has to be used cleverly. That is what the lecture of Professor Debashish has shown. With this, I thank Professor Debashish for agreeing to deliver this fantastic lecture. And I hand over the stage to Manas. Thank you.
Wow, that was a wonderful evening with an amazing lecture, sir. Thank you so much. I'm extremely thankful to all the senior professors here in this talk. More than 36 students from IIT Bombay participated in it, and it was a very insightful lecture. I would like to also extend my thanks to Professor Sudarshan Kumar for moderating this talk and presenting us with this very amazing opportunity. Debasis Chakraborty sir, thank you so much for taking out time to deliver this wonderful lecture and giving us some knowledge and shedding light on the fields of propulsion technology and hypersonic flights and what DRDO is doing in the field for advancing the technology. Thank you so much, sir.
Thank you.